So good afternoon. In this presentation, I will show two case studies on summer comfort in Belgian dwellings which have no active cooling system. I will first very briefly introduce myself. I'm from the Energy Knowledge Center, which is part of Thomas More. So we are in Geel, Belgium. We are a center of expertise that focuses on energy systems in buildings and energy systems in greenhouse horticulture. You can find there our website and maybe more interesting, the Coronet Schools website. And there you can find, apart from the two case studies that I will present today, some other results of the school's research project. So it was about sustainable cooling systems in a residential context. Then about the case studies, I will look at two new built Belgian dwellings. You can see them here on the pictures. So they are good insulated, they have good air tightness, they both have a mechanical ventilation system with heat recovery and a summer bypass. And of course, they are both equipped with some low energy cooling strategies and cooling systems. So they both have a geothermal heat pump. Like usually it is dimensioned basically based on the heat demand, but as you can see here, it allows some free cooling when the heat pump is bypassed. Then the most important emitter is floor cooling. And it is also the most powerful one. But in the first dwelling, we also have a cooling coil in the supply of the ventilation unit. It is also connected to the free cooling. And then in the second dwelling, we also have some cooling on the ventilation unit, but there we have some evaporative cooling on the extraction pipe of the ventilation unit. Then we did measurements in the summer of 2019 and 2020. So we had the opportunity to measure during 3 heat waves. On the graph, you can see in yellow measurements over whole year for 2090. And then I added in black as a reference the TMY file for UCL. So then you see very clearly the two heat waves. The second one was very extreme for us. We had temperatures going to 40 degrees. And you can also see that in general, temperatures are much higher than what we're used to. So for these case studies, I will first and principally show something about the comforts evaluation. And then if I have some time left, I will add some practical issues and some lessons learned. So I start with the comfort for the first case. Here I have some more detailed information. So the facade has a southwest orientation. And then on the other side, it has also windows on the northeast side. It has an average glass to floor ratio of 14%. There are no screens, but as you can see on the picture, you have some overhangs that give some shadow on the windows. Then, like I said, we have a heat pump. It has 2 boreholes of 100-meter depths each. All rooms have floor cooling, and in 2020, a cooling coil in the ventilation unit was added. So when we look at the temperature measurements, here you see on the x-axis temperature, on the y-axis the relative occurrency for the living room, and then in blue for 2090, in orange for 2020. And I will first use a comfort criterion that is based on Wenger that you can find in these standards. It is with fixed limits. So there is a first category that is limited at 25.5, a second at 26, and a third at 27 degrees. And then when I add the exceeding hours, then you can see that we are always within category 2. So this means that we expect to have less than 10% of dissatisfied. Then I can show a similar graph for the sleeping rooms. Here we are always within category 3. You see that here we have more difference between the 2 years. So in 2020, the cooling coil in the ventilation unit was added, and apparently the effect of supplying fresh air had more impact in the sleeping room than in the living room. So in the previous slides, I worked with a comfort criterion with fixed limits according to Fanger, but it was shown that if you have what we call an alpha building, so where occupants can open windows or influence the indoor climate, that well, higher indoor temperatures are accepted than according to Fanger. It's interesting to use some adaptive temperature limits on this case. So I have here the same temperature measurements as in the previous slide, but now on the x-axis, I have the running mean outdoor temperature. So this means that when we have 16 degrees, we are in summer, and when we are at 22, we have a hot summer period, and then here we have the heat waves. And then when I add the adaptive temperature limits, we see that during the heat waves, we meet very easy those adaptive criteria. Then, of course, temperature is not the only influencing factor when we talk about comfort. So I added here on the x-axis measurements of the relative humidity. I have again these three comfort categories according to Fanger, so with fixed limits. And then we see that apparently relative humidity is more problematic here than temperature was. But I have to add two remarks. The first one is that in this specific dwelling, there were a lot of plants and laundry was drying in the living room and so on. So I think relative humidity was quite high. And another remark is that the occupants did not the summer comfort in the dwelling. So I think that here again, these fixed limits are maybe a bit too severe for a residential context. Okay, then let's have a look at the second case. It is very similar. Here again, we have a glass to floor ratio of 12%. It's a detached house now, so we have windows at the four facades. And here we have automatic solar shading. We have one borehole of 120 meters and all rooms with floor cooling. And here we had the evaporative cooling. So maybe let's first have a look at this graph. You see in red the outdoor temperature and in blue the indoor temperature. And what happened here is that in the blue indicated period, the occupants went on holiday. So the sun shading was not used anymore. And then in the green indicated period, the floor cooling was turned off. And it was just at the moment that we had that extreme heat wave. So you see that after the floor cooling was turned off, within 3 days, we are exceeding temperature limit of 27 degrees. Then it is cooling down outside. But then you see that even if here your outdoor temperature is similar to what we had before the heat wave, that your indoor temperatures stay quite high. We're going to that 26, 27 degrees. And it's only here when your floor cooling was turned on again, that we're going back inside to those very comfortable temperatures of 22, 23 degrees. So when I show again the same histograms, you see here what happened when the floor cooling was turned off, but when I leave out those measurements, then we have similar results as in the previous dwelling. And the same for the sleeping room. So I think it are quite good results. And then I compared it again to the adaptive temperature limits. And there we see that even when the cooling was turned off during that heat wave, that we are still meeting those adaptive criteria, except here we have some exceeding hours, but that's of course, when I come back to that graph, that's of course what happened here, that it cooled down outside, but that inside we had still those quite high temperatures. So I think we can conclude that for the two new build dwellings that we measured, and which are equipped with a ground source cooling system, that they are future proof. But I want to refer to this paper of Abantika Sengupta of KU Leuven. In fact, she used the same case studies as I presented to investigate the impact of future climate on the performance of ground source cooling systems. And in fact, so we can say that the weather that we had in 2020, the temperature and the solar radiation was quite similar to what we see in future midterm scenarios. But she shows that for these dwellings, for these case studies, we might expect more exceeding hours with such a midterm future scenario, because there you have the fact that your ground source is warming up. And that's of course something that we cannot consider in the measurements. So that was about the comfort evaluation. Then I'm going to add some lessons learned or practical issues. So I start with some points that are about the condensation risk, the fact that you want to avoid condensation. So here, for instance, I have the measurements of the evaporative cooling, after the evaporative cooling, the relative humidity is limited at 78% because we want to avoid condensation in the pipes here. But then what you see at the measurements, in blue we have the outdoor, and in gray the indoor temperature, and then in orange here the supply temperature of your ventilation unit. And then we see that when the outdoor temperature is going to, let's say, 26, 27 degrees, the supply temperature is higher than the indoor temperature. So you don't have a resulting cooling effect. That's not what you want. So then we increased here the set point to 90%. And I think the installation is still working with that set point, and it didn't cause any problems. And then we see that after that intervention, we had that extreme heat wave. And even then, the supply temperature was lower than your indoor temperature. So that's the first example. Then when you have floor cooling, we also want to avoid condensation on the floor, of course. So we have usually a dew point control. And that's what you see happening in this graph too. So in blue, we have the temperature of the ground source, which was always around 16 degrees. Then after the heat exchanger, we have here the supply temperature to the floor cooling, which is about 19 degrees. And then in yellow, we have the return, which is about 21 degrees. And then you see at the indicated points that in fact the heat exchanger with your source is bypassed because there was a condensation risk. So, but we saw that in those two dwellings that we measured, it didn't happen very often. And in fact, control or the risk of condensation was not really a limiting factor to the performance of your floor cooling. Of course, this can be different maybe in a non-residential case. This is a completely different case. It's an office room with ceiling cooling, but just to show you that here, when you have higher relative humidities indoor, that your dew point control is working maybe more. So here you see in blue and in orange the temperature of the water that is going in and coming out of your ceiling. And you see clearly that it works on off. And there maybe it would be more interesting to just increase your supply temperature to avoid as a function of your dew point instead of having this on-off functioning. And then I think this will be the last example. It's again on the control of the evaporative cooler. So I will show again some measurements. In blue, we have the outdoor temperature. In black, we have the indoor temperature. And then in red, that's the temperature after the evaporative cooler. So you see that your temperature drops with about 4 degrees. And in orange, we have the supply temperatures. So I showed already that it worked quite good. But in the indicated periods here, we see that, well, your temperatures inside are quite high, but the bypass was not used. It would have been better here to just supply the outdoor temperature. So what happened here is that the sensor that measures the indoor temperature is situated here at the entrance of your heat recovery. And so it measures the red temperatures, which is quite low, and it concludes that, well, in fact, there is no cooling needed, so the bypass shouldn't work. So this is, I think, an example that it is important when you combine systems to just watch out that your control is working good. And I think that my time is left now, so so thank you for your attention. And if you have some more questions or you want some more information about the case studies, you can contact me.